February 18th, 1943, a Lancaster bomber limps home through the night sky with 3 engines dead and over 200 bullet holes. 7 men aboard should be dead. Instead, they're about to land. This is the story of the impossible. If you're fascinated by incredible WWII survival stories, like this video and subscribe for more untold tales of courage and engineering miracles. 21:30 hours. 14,000 feet above the North Sea. The wireless operator's fingers were numb. Flight Sergeant Thomas Chapman had been airborne for 4 hours, and the temperature inside the Lancaster had dropped to minus 20 degrees Celsius. Outside the perspex window, darkness consumed everything. The kind of absolute black you only find at 14,000 feet over the North Sea on a moonless night in February 1943. His breath formed ice crystals on the radio equipment as he logged their position. 52 degrees north, somewhere over hostile waters, precisely where Bomber Command had never intended them to be. Lancaster ED-588, christened Q for Queenie by her ground crew, struggled eastward on dying engines. She was a Mark I variant, fresh from the Avro production line at Chatterton, with barely 60 operational hours on her airframe. Her 4 Rolls-Royce Merlin engines had once produced a combined 5,280 horsepower, pushing 30 tons of aircraft, fuel, and high explosives toward the Ruhr Valley. Now, only one engine maintained full power. The starboard inner had seized completely. The starboard outer ran rough, missing on at least 2 cylinders. The port outer showed oil pressure readings that meant imminent failure. The steady drone of 4 Merlin engines had become an irregular heartbeat, each missed beat counting down to silence. In the cockpit, 23-year-old Flight Lieutenant David Mitchell held the control yoke with hands that hadn't stopped shaking for 2 hours. The aircraft wanted to roll right continuously, pulled by the asymmetric thrust of the failing engines. His left leg cramped from constant pressure on the rudder pedal, fighting to keep Q for Queenie's nose pointed toward England. Mitchell knew the statistics that Bomber Command's analysts calculated with clinical precision. Of every 100 aircrew who began operational tours, fewer than 25 would complete 30 missions. The rest would die in burning aircraft over Germany, drown in the North Sea, or spend years in prisoner of war camps. Tonight, Mitchell and his crew had joined those statistics. The question was which category. Behind him, the rest of the crew occupied their battle-damaged stations. Navigator Flight Sergeant James Hartley hunched over charts soaked with hydraulic fluid, plotting their course by dead reckoning because the astro-navigation equipment had been destroyed. The red glow from his desk lamp, designed to preserve night vision, now illuminated calculations that meant the difference between reaching England and dying in cold water. In the mid-upper turret, Sergeant Peter Walsh rotated his Fraser-Nash turret through endless arcs, searching for German night fighters. His left shoulder bled steadily from shrapnel wounds, but he maintained his watch. The rear gunner, Sergeant Ronald Davies, did the same from his isolated position in the tail. The loneliest and coldest spot in the entire aircraft, now made colder by 3 separate holes in the turret's perspex canopy. The bomb aimer, Flight Sergeant George Patterson, had crawled back from his prone position in the nose after completing the bomb run over Essen, the Norden bomb site. Precision instrument worth more than most men's annual salary lay in pieces, destroyed by a 20mm cannon shell that had missed Patterson's head by inches. The flight engineer, Sergeant Arthur Collins, stood beside Mitchell's seat, monitoring engine parameters that told a story of mechanical death approaching with mathematical certainty. They had taken off from RAF Skellingthorpe in Lincolnshire at 18:20 hours, part of a stream of 314 bombers heading for the Ruhr Happy Valley, the crews called it, with the bitter irony that kept men sane when facing industrial-scale death. The Ruhr was the most heavily defended target in occupied Europe, ringed by more than 1,500 heavy flak guns pointed skyward, served by experienced crews who had been tracking and destroying British bombers since 1940. Each gun could fire 15 rounds per minute to an effective ceiling of 26,000 feet. Each shell contained 1.5 kilograms of high explosive wrapped in steel designed to fragment into thousands of white-hot shrapnel pieces. Bomber Command knew Every raid on the Ruhr would cost them aircraft. Air Chief Marshal Arthur Harris and his staff calculated casualties with actuarial precision, weighing bomber losses against strategic objectives. Tonight's target was the Krupp steelworks in Essen, vital to German tank production, worth the human cost that Harris knew would result. The control yoke vibrated in Mitchell's hands like a living thing in pain. Each tremor transmitted from engines dying in the darkness. German workers, French and Belgian forced laborers, women and children living near the factories. They understood it, accepted it, and tried not to think about it. Such was the mathematics of total war in 1943, when survival itself had become a victory. The first shell had detonated 40 meters below the Lancaster's belly, close enough that the blast wave lifted the entire aircraft 3 feet upward in a sickening lurch. Mitchell felt the control yoke wrench in his hands as Q for Queenie bucked like a wounded animal. The explosion's orange flash lit the cockpit for a fraction of a second before plunging them back into darkness. Then the next shell arrived, and the next, and suddenly they weren't flying through empty sky anymore. They were flying through a constellation of fire. German 88mm Flak 36 guns could maintain a rate of fire that turned the sky into a geometry of death. Each shell's time fuse was set based on radar tracking and optical range finding, calculated to detonate at precisely the altitude where British bombers flew. When a shell exploded, steel fragments spread outward at supersonic speed in a lethal sphere roughly 50 meters in diameter. Being caught in one burst was catastrophic. Being caught in a barrage meant fragments from multiple shells converging from every direction simultaneously, creating zones where survival was statistically impossible. A piece of shrapnel the size of a man's thumb punched through the fuselage behind Walsh's turret, the metal so hot that it ignited the fabric insulation as it passed. Another fragment, this one 8 inches long, tore through the port side and exited through the starboard, missing Chapman's head by inches and destroying his primary radio set in a shower of sparks and shattered vacuum tubes. The Lancaster's thin aluminum skin, barely 2 millimeters thick in most places, and designed for weight saving rather than protection, offered no meaningful resistance to the shrapnel. Each fragment that struck the aircraft either passed completely through or lodged itself in whatever structure lay behind the outer skin, creating damage that accumulated with each near miss. In the rear turret, Davies saw the fighter, a Messerschmitt Bf-110G night fighter, designated C9+EN from IV/NGG-1, attacking from below and behind, exactly the angle German pilots preferred because it placed them beneath the effective arc of the Lancaster's dorsal turret. Oberlieutenant Wilhelm Jonen had guided his twin-engine fighter into position using Liechtenstein airborne intercept radar, technology the British didn't yet fully understand. The Germans were winning the night war in early 1943, their radar-equipped fighters claiming an increasingly devastating toll on bomber command. Davies hammered his 4 Browning machine guns into action, each weapon firing .303 rounds at 1,150 rounds per minute. The tracer rounds arced downward in brilliant streams, but Jonen wasn't where the tracers went. He had already rolled his Bf-110 30 degrees to port, positioning himself for a deflection shot with his forward-firing armamentation. When Jonen pressed his firing button, the result was devastating. 20mm cannon shells are not bullets. They are miniature artillery rounds, each one containing high explosive that detonates on impact. The first shell struck Q for Queenie's starboard horizontal stabilizer, blowing a hole the size of a dinner plate through the control surface. The second and third shells walked up the fuselage, each one creating an explosion that sent shrapnel ricocheting through the interior like deadly hail. Machine gun rounds followed, punching neat holes through the aluminum skin, entrance holes the size of a sixpence, exit holes twice as large where the bullets tumbled and tore the metal. The Merlin engine's synchronized rhythm became discord, 4 voices becoming 3, then 2, then 1 desperate song against the night. Patterson, lying in the nose, felt the entire aircraft shudder as rounds stitched across the forward fuselage. One bullet passed so close to his head that he heard the supersonic crack, a sound like a whip snapping inside a tin can. Another round struck the bomb sight mechanism, destroying the delicate optics that allowed precision targeting. In that moment, Patterson knew their mission was finished.
They couldn't bomb accurately without the sight, and continuing to the target would be suicide. Mitchell fought the controls as the Lancaster's nose tried to drop. The shells had damaged the elevator cables, introducing slack into the system that made the aircraft respond sluggishly, unpredictably. Banking the bomber to port, away from the searchlights and flak, he pushed the throttles forward, asking the Merlins for every available revolution. The engines responded with their characteristic roar, but something was fundamentally wrong. Oil pressure on the starboard inner engine was fluctuating wildly, and the coolant temperature was climbing toward the red line. By any reasonable calculation, by the engineering standards that governed aircraft design, Q for Queenie should have been tumbling earthward in pieces. Yet she flew. And understanding why requires understanding what aircraft designers in 1941 knew about keeping bombers alive over Germany. Roy Chadwick, chief designer at Avro, had studied every bomber loss report from the early war years, cataloging how and why aircraft failed. His conclusions fundamentally shaped the Lancaster's design philosophy. Redundancy, not armor, would save crews. Consider the control systems first. When a pilot moves the control column in a Lancaster, he isn't directly moving the control surfaces. That would require impossible physical strength at high speeds. Instead, he pulls steel cables that run the length of the fuselage through pulleys and fair leads, eventually connecting to elevators, rudder, and ailerons. Chadwick's genius was installing dual cable runs for critical controls. When shrapnel severed the primary elevator cable on Q for Queenie's port side, the starboard cable still functioned, providing Mitchell with degraded but functional pitch control. A single cable system would have meant immediate loss of control and certain death for all 7 crew members. The same principle applied to the hydraulics. Lancaster hydraulic systems operated at 1,000 pounds per square inch, powering landing gear, flaps, and bomb doors. The system used 2 independent pumps driven by separate engines with accumulators storing pressure for emergency use. When fragments punctured the main hydraulic line running beneath the cockpit floor, fluid sprayed across the interior in a fine mist. But the secondary system maintained sufficient pressure for basic operations. Engineers at Avro had calculated that even with 70% system loss, enough pressure remained for 1 landing gear extension, assuming the crew survived long enough to need it. The structural design itself embodied lessons written in the wreckage of Wellingtons, Hamdens, and Whitleys. The Lancaster's fuselage was a semi-monocoque structure, meaning the outer skin carried aerodynamic loads while an internal framework of formers and stringers provided rigidity. When a shell fragment punctured the skin, it created localized failure, but surrounding structure redistributed the stress loads automatically. Think of it like a fishing net with several holes. The net still functions because load transferred to adjacent strands. Q for Queenie had taken hits that removed perhaps 4 square meters of skin in total, but 96% of her structure remained intact, continuing to carry the loads that kept her airborne through principles of structural engineering that wouldn't be fully understood until decades later. The oil pressure gauge became Mitchell's universe, its needle dropping like hope itself, each pound per square inch a countdown to silence. The engines presented the most critical vulnerability. Each Merlin XX produced 1,280 horsepower at 3,000 revolutions per minute. A precisely balanced dance of exploding fuel and moving metal parts operating at temperatures that would melt copper. The engine's cooling system circulated 70% water, 30% ethylene glycol through passages in the cylinder heads and block, dissipating tremendous heat generated by combustion. When shrapnel punctured the coolant jacket on the starboard inner engine, superheated coolant flashed into steam and the temperature gauge began climbing toward destruction. Collins, watching the needle approach 135 degrees Celsius, knew they had perhaps 15 minutes before the engine seized, pistons expanding from heat until they welded themselves inside their cylinders. But here again, redundancy philosophy saved them. The Lancaster didn't need all 4 engines. She could maintain altitude on 3, even limp home on 2 under ideal conditions. Collins adjusted the mixture controls, enriching fuel flow to the damaged engine to provide some cooling effect through evaporation, while Mitchell reduced power to decrease heat generation. The oil pressure concerned Collins more than temperature. Oil not only lubricated, but also cooled, and falling pressure meant bearing surfaces were running metal on metal, generating heat that would destroy the engine within minutes. He watched the pressure gauge drop from 90 pounds per square inch to 70, then 60. At 40, he would have no choice but to shut the engine completely down. The fuel system demonstrated another layer of survival engineering that separated the Lancaster from earlier designs. The aircraft carried 2,154 imperial gallons of high-octane aviation fuel distributed across 14 tanks located in wings and fuselage. No single point of failure could drain the entire supply, a lesson learned painfully during early war operations. Self-sealing technology, developed frantically in 1940 after the Battle of France demonstrated fuel tank vulnerability, consisted of multiple rubber layers. Untreated rubber on the outside, unvulcanized rubber next, then vulcanized rubber, and finally synthetic rubber on the inside facing the fuel. When a bullet punctured the tank, solvents in the fuel caused unvulcanized rubber to swell, plugging the hole within seconds. Q for Queenie had taken at least 8 bullets through her wing tanks, but she was losing fuel at perhaps 7 gallons per hour rather than the catastrophic hundreds that would have resulted without self-sealing technology. This gave them range to reach England, assuming the engines continued running long enough to burn that fuel. Mitchell's world had narrowed to instruments and instinct. The artificial horizon showed Q for Queenie banking 4 degrees to port, not through any input he had given, but because damaged tail surfaces created asymmetric drag. Every few seconds, he corrected with right aileron, a constant wrestling match with an aircraft that no longer flew straight. The airspeed indicator read 185 miles per hour, 30 miles per hour slower than normal cruise speed. They were dragging through the sky now, bullet holes and torn metal creating turbulence that buffeted the airframe and increased fuel consumption by roughly 20%. His feet worked the rudder pedals continuously, compensating for yaw created by the damaged starboard inner engine. Collins had reduced power on that engine to 60%, which meant the port inner had to produce more thrust to maintain balanced flight, which meant it was consuming more fuel, which meant their range was shrinking with every minute airborne. The mathematics were brutal and simple. The control yoke had become an extension of Mitchell's will, transmitting every vibration from dying engines, every structural stress, every moment closer to catastrophic failure. They had burned fuel getting to the Ruhr. They had burned more maneuvering through flak and fighter attacks. And now they were burning it faster than planned getting home. Hartley would need to calculate whether they had enough to reach England, and his calculations would determine whether 7 men lived or died in the North Sea. In the navigator's compartment, Hartley was already performing those calculations, his pencil moving across charts with practiced efficiency despite hands that trembled from adrenaline and cold. They had turned back at 51.8 degrees north, 7.2 degrees east, roughly over Münster in occupied Germany. RAF Skellingthorpe lay at 53.2 degrees north, 0.5 degrees west. The straight-line distance was approximately 320 miles, but they couldn't fly straight lines over occupied Europe. German night fighters patrolled known routes, and certain areas were so saturated with flak batteries that only suicidal pilots would cross them. Hartley drew a dogleg course northwest to the coast, then west across the North Sea, approaching Lincolnshire from the northeast, where British radar could identify them positively. Total distance 365 miles. At their current reduced speed of 185 miles per hour, that means just under 2 hours flying time. Now for the fuel calculation that would determine their fate. They had started with 2,154 gallons. Approximately 3.5 hours of flying had consumed roughly 1,200 gallons at normal consumption rates. The maneuvering and higher power settings during the attack had cost them another 100 gallons. The leaking tanks were losing perhaps 7 gallons per hour. That left approximately 850 gallons remaining. At their current consumption rate of roughly 450 gallons per hour due to damage and asymmetric power settings, they would burn about 900 gallons, reaching Skellingthorpe. The mathematics were unforgiving. They were 50 gallons short of fuel needed to reach England. But Hartley's calculations assumed the starboard inner engine kept running. If Collins had to shut it down, fuel consumption would actually decrease slightly, but they would lose altitude and airspeed, possibly making England unreachable for aerodynamic rather than fuel reasons. Collins's voice cut through the intercom static. "Skipper, oil pressure on starboard inner is down to 35 pounds and dropping. Temperature at 132 degrees Celsius. Mitchell processed the information instantly. The engine was dying. They might get another 5 minutes from it. Maybe 10 if they were extraordinarily lucky. After that, they would be on 3 engines with 280 miles still to go."
He eased the throttle back further on the failing engine, reducing power to 30%. Every revolution he could save might be the difference between reaching England and adding 7 more names to Bomber Command's casualty lists. The decision that saved them came from an unexpected source. Davies, isolated in the rear turret and fighting hypothermia from 3 holes in his canopy, reported what he thought was another night fighter approaching from astern. Mitchell immediately descended 2,000 feet and increased power on the remaining engines, a maneuver that should have consumed more fuel, but actually improved their situation. The lower altitude reduced the load on the engine significantly. Air density at 12,000 feet was 20% greater than at 14,000 feet, which meant the Merlins could produce the same power with less throttle opening, consuming less fuel per mile. The contact Davies had seen turned out to be a piece of debris from their own aircraft, torn loose during the fighter attack, but the altitude change had bought them the fuel margin needed to reach England. 4 Merlin engines had become 3, their synchronized song becoming harmony, then discord, then desperate solo performance against the infinite darkness. 30 minutes into their journey home, the starboard inner engine finally seized. Collins watched oil pressure drop to 0 and temperature climb beyond the gauge's red line before shutting down the engine completely. He feathered the propeller, rotating the blades to minimum drag position, and the Lancaster yawed sharply to starboard as asymmetric thrust tried to pull them into a turn. Mitchell stamped full left rudder, his leg muscles straining against the pedal, then retrimmed the aircraft using the rudder trim wheel beside his seat. Even with trim, he would need to maintain constant pressure on the rudder pedals. His left leg would be burning with fatigue before they reached England, but that was a problem for the living. He advanced throttles on the 3 remaining engines, asking them for power the starboard inner no longer provided. The Merlins responded, but Collins watched fuel consumption climb. They had just lost their safety margin again. Every mile now counted. Every decision carried life-or-death consequences. The Dutch coast appeared as a darker line against dark water, visible only because Walsh spotted white foam where waves broke on beaches. They were leaving occupied Europe behind, entering the relatively safe expanse of the North Sea. Relatively safe, because the water temperature in February hovered around 5 degrees Celsius. A man in that water would lose consciousness from hypothermia within 15 minutes, death following within 30. Ditching a Lancaster in darkness in those conditions was tantamount to executing 7 men, but it remained their only option if the remaining engines failed before reaching England. Mitchell maintained 12,000 feet, high enough to glide considerable distance if another engine quit, low enough to conserve fuel. The artificial horizon showed them tracking roughly west-northwest, the magnetic compass steady on 285 degrees. Below them, the North Sea stretched gray and infinite, even in darkness, conveying its lethal indifference to human survival. Collins monitored engine parameters with the intensity of a man whose life depended on cylinder head temperatures and oil pressures, which it did. The port outer engine was running hot, not dangerously so yet, but showing early signs of the cooling system damage that had killed the starboard inner. The port inner ran smoothly, but fuel pressure was fluctuating slightly, suggesting possible pump problems or contamination in the fuel lines. The oil pressure gauge had become a timepiece, measuring not hours or minutes, but heartbeats of machinery slowly dying in the hostile sky. Only the starboard outer engine ran normally, and it was carrying load far beyond design specifications, working harder than any Merlin was meant to work for extended periods. Collins knew that engine could fail at any moment from simple mechanical fatigue, leaving them with two engines that might not provide enough power to maintain altitude with their current weight and battle damage. Chapman finally managed to raise RAF Skellingthorpe on his backup radio. The signal was weak, breaking up, but communication was possible. Skellingthorpe Control, this is Queenie, inbound on 3 engines with battle damage, requesting priority landing. The response came back faint but clear. Queenie, Skellingthorpe Control, roger your priority, weather Kavak, wind 270 at 8 knots, cleared to land runway 27. Fire and ambulance will be standing by. Kavak meant ceiling and visibility okay. At least the weather was cooperating. They would land in clear conditions with minimal wind. Small mercies in a night full of disasters. 50 miles from the English coast, the electrical system began failing intermittently. Lights in the cockpit flickered, dimmed, then brightened again as generators struggled to maintain voltage. The Lancaster's electrical system ran on 24 volts DC, supplied by generators on each engine. With one engine shut down and another running rough, the remaining generators were carrying the full electrical load. Landing lights, instrument lights, radio, navigation lights, gun turret heaters, oxygen system pumps. Collins started shedding electrical load systematically. The turret heaters went first. Walsh and Davies would have to endure the cold for another hour. Navigation lights next. They would need those only in the landing pattern. Every amp he could save reduced strain on the remaining generators and decreased the probability of total electrical failure that would leave them flying blind in darkness. The Lincolnshire coast materialized as a scatter of dim lights, blacked out villages showing just enough illumination to prevent aircraft collisions while denying German bombers navigation references. Hartley identified Skegness by the distinctive bend in the coastline, then traced their position inland toward their home base. 12 miles to Skellingthorpe, Mitchell began his descent, reducing power gradually, letting Q for Queenie settle earthward at 300 feet per minute. Every reduction in power saved fuel, but it also meant less margin if something went wrong during the approach. At 8,000 feet, Collins reported they had approximately 180 gallons remaining, enough for 25 minutes at current consumption, more than sufficient unless the landing went badly. The runway lights at Skellingthorpe appeared at 5 miles distance. 2 parallel rows of dim blue lamps outlining runway 27, oriented 270 degrees, almost due west. Mitchell clicked his transmit button. Skellingthorpe Tor, Queenie on final approach. The response came immediately. Queenie, you are cleared to land. Fire equipment in position. Along the runway's edges, Mitchell could see fire tenders with their crews standing ready with foam equipment. If Q for Queenie caught fire on landing, they would have perhaps 90 seconds to douse flames before fuel tanks exploded. Everyone knew the statistics. Post-crash fires killed more airmen than the crashes themselves. The control yoke trembled with 3 engines' labor. No longer the smooth authority of 4 Merlins in harmony, but the desperate struggle of machinery pushed beyond all reasonable limits.
At 2,000 feet, Mitchell called for landing checks. Collins ran through the abbreviated list. Hydraulic pressure barely sufficient for 1 gear extension. Fuel sufficient for approach only. Mixture rich on all running engines. Propellers set for landing. The bomb bay still carried their full load. They had flown 350 miles with live explosives aboard because jettisoning over occupied territory or the North Sea had presented worse options than landing with them. Now Mitchell had to decide, land with the bombs or jettison them onto the grass beside the runway. He chose to keep them. Jettisoning created risk of detonation that might damage the runway or kill ground personnel. Better to land carefully and let armorers safe the weapons on the ground, assuming they survived the landing attempt. At 1,000 feet, Mitchell lowered the landing gear. Hydraulic pumps whined as fluid flowed through damaged lines, pushing heavy gear assemblies downward against aerodynamic loads and mechanical resistance. The port main gear locked down with a reassuring thunk that transmitted through the airframe. The tail wheel dropped and locked normally. 3 green lights illuminated on the instrument panel, but Mitchell knew the hydraulic system was operating at absolute minimum pressure. If he had to go around for a second approach, the gear might not retract. creating drag that would make climbing away impossible with only 3 engines. Collins cross-checked visually, craning to see the port gear through his side window, confirming the indication. Davies in the tail reported the tail wheel appeared down and locked. One critical hurdle cleared, but several remained. At 500 feet, Mitchell extended flaps to 15 degrees. The Lancaster's flaps were massive control surfaces that, when fully extended, increased wing area by 20% and drag enormously. But the marginal hydraulic system couldn't handle full flap extension, and asymmetric flap deployment would roll them inverted at low altitude. He held at 15 degrees, accepting faster approach speed rather than risking flap failure. Approach speed would be 120 miles per hour instead of the normal 95. Faster, but manageable if he used the entire runway length. The runway rushed up to meet them, concrete painted with blue lights stretching into darkness. Mitchell pulled the throttles back to idle on the 3 running engines, feeling Q for Queenie settle into ground effect, that cushion of compressed air between wings and earth that gives pilots one last chance to correct mistakes. The main wheels touched first. Firm contact that wasn't graceful but was effective. Then the tail wheel settled as Mitchell eased the control column forward. They were down, rolling, alive. But they weren't safe yet. At 120 miles per hour on a 6,000-foot runway with marginal brakes, stopping required precise calculation and considerable luck. Mitchell applied brakes gradually, feeling the aircraft decelerate. The starboard brake felt spongy, probably damaged by shrapnel, but it was slowing them. 100 miles per hour, 80, 60. They would stop with runway to spare. Collins shut down all engines, pulling mixture controls to idle cutoff, watching propellers windmill to a stop as Q for Queenie rolled to a halt 4,800 feet down the runway. Fire crews converged on the aircraft immediately, spraying foam across hot metal as a precautionary measure. Mitchell shut down all remaining systems, watching instrument lights die one by one as electrical power ceased. His hands shook now that tension had released, adrenaline having nowhere to go. The silence was profound after hours of engine noise, broken only by cooling metal contracting, the aircraft herself sighing of relief at journey's end. They climbed out through the main door onto the wing, then slid down to concrete on legs uncertain after 5 hours airborne. An ambulance crew rushed to Davies, whose face had gone gray from cold and blood loss from wounds no one had known about. Shrapnel had caught his arm during the initial attack, and he had said nothing for 350 miles. Walsh limped, favoring his left leg where shrapnel had torn his thigh. Chapman's ears were bleeding from the concussion of exploding shells. The rest bore invisible wounds that would surface in dreams and sudden panics for decades to come. The price of surviving what should have killed them. Behind them, Q for Queenie sat broken on the taxiway, hydraulic fluid pooling beneath her wounded frame. In morning light, ground crews would count 287 separate impacts on her structure, catalog damage that by every engineering principle should have been fatal. But she had brought 7 men home alive, and in February 1943, that made her one of the most successful bombing missions of the war. Chief Technician Harold Webster walked the length of the fuselage at dawn, counting impacts, cataloging destruction. The rudder showed 23 separate perforations, the elevators 31. The port wing displayed 54 holes, ranging from pencil-sized bullet punctures to jagged tears where shell fragments had ripped through aluminum skin. One fragment had passed within 3 inches from the main spar, the structural member carrying the wing's entire load. 3 inches different, and the wing would have folded, tumbling Q for Queenie into Germany at 200 miles per hour. Webster's final count reached 287 separate impacts, 198 from machine gun fire, 89 from shell fragments and shrapnel.
The numbers told only part of the story. Inside the fuselage, Webster found damage that should have been catastrophic. Severed control cables hanging loose, electrical wiring cut through, hydraulic lines punctured, oxygen bottles holed and empty. The starboard inner engine, when examined closely, had taken 4 separate hits. One bullet had passed completely through the crankcase, leaving entry and exit holes that should have drained all oil within minutes. Instead, the engine had run for nearly 2 hours before finally seizing. Engineers from Rolls-Royce would study that engine for months, trying to understand how it had continued operating with such
such massive internal damage. The story of Q for Queenie spread through Bomber Command like wildfire, passed from aircrew to aircrew in briefing rooms and mess halls across England. Here was proof that the Lancaster could absorb phenomenal damage and still fly, that skilled crews could bring home aircraft that should have been lost with all hands. But the story also revealed the brutal mathematics of the bomber war. Of the 314 aircraft that had set out for the Ruhr that night, 23 failed to return. That was 161 aircrew killed or missing. 23 crews who didn't have Q for Queenie's combination of structural resilience, crew skill, and simple luck. The transformation in aircrew morale was immediate and measurable. Stories of miraculous survival spread faster than official communications, carried by replacement crews arriving from training units, passed along informal networks that connected every RAF base in Britain. If Q for Queenie could make it home with 3 engines dead and 287 holes, then perhaps survival wasn't purely a matter of luck. Perhaps skill, determination, and aircraft design could tip the odds in favor of the living. Training programs began emphasizing emergency procedures that had been theoretical before Q for Queenie proved them practical. Engineers studied her damage patterns, learning where additional redundancy might be built into future aircraft designs. The psychological impact reached beyond technical considerations. Aircrew who had accepted 25% survival rates as immutable began to believe that survival was possible, that their aircraft could bring them home even after absorbing damage that should have been fatal. This transformation in morale coincided with improvements in fighter escort, radar technology, and German defensive capabilities. By late 1943, Bomber Command's loss rates had begun declining from their early war peaks, though they remained horrifically high by any reasonable standard. Q for Queenie had become a symbol of resilience, proof that well-designed aircraft flown by skilled crews could survive the apparently unsurvivable. Flight Lieutenant David Mitchell completed his tour of 30 operations 3 months later, one of the 25% who survived their full commitment. He was awarded the Distinguished Flying Cross for bringing Q for Queenie home, though he always insisted the medal belonged to his entire crew. The aircraft herself was repaired and returned to operational service within 6 weeks, her battle damage patched with aluminum plates and new components. She flew 43 more missions before war's end, never again suffering damage as severe as that February night over the Ruhr. Her final tally? 97 operational sorties, more than 500 hours over enemy territory, and every single crew member who flew in her brought home alive. In the mathematics of aerial warfare, where the most bombers were lost after fewer than 20 missions, Q for Queenie's record bordered on the miraculous. In the mathematics of war, the impossible becomes merely improbable, and the improbable becomes achievable through skill, determination, and the stubborn refusal to quit. In the end, the true measure of any weapon system is not its destructive capability, but its ability to preserve the lives of those who operate it. By that measure, the Lancaster bomber, and Q for Queenie in particular, achieved something far more valuable than military victory. They achieved the preservation of human courage itself, ensuring that future generations would know that even in the darkest moments of history's darkest war, ordinary men could accomplish extraordinary things. The drone of Merlin engines faded into history, but the lesson of Q for Queenie endures, that the human spirit, properly supported by sound engineering and unwavering determination, can survive anything that war and circumstance can devise.